Hi, today we will talk about what perfect square numbers are and why and how they actually work. First, I would like us to recall some major vocabulary. Look at the expression on the left side of the screen. Square root of 9 equals 3. Well, first of all, I'd like to attract your attention to the fact that square root of 9 could be written in the following form. You now notice an index of 2. Normally, when we are talking about square root, this 2 is not written, but it's silently meant right here in the place of an index. There are 3 places where I would like you to identify appropriate vocabulary words. The first one is pointing at the sign whose name is radical. Radical represents this symbol. 9 itself, the expression under the radical sign, is called a radicand with nd at the end, radicand. You also notice that there is a synonym to something that we call radicand. In our case, we could say that 9 is a square of a 3. And the result of this expression, the 3, is referred to as a square root of 9. It is very important not to get confused between these two vocabulary words, square root of something and square of something. It's very important to know how to use the notation of a radical sign correctly. It has to be long and tall enough to clarify what it is that you exactly mean. For example, the expression on the left, the way it's written, could mean that you're taking a square root of x and then adding 4, or could mean that you're taking a square root of the entire expression, x plus 4. In order to be clear with what exactly you mean, your radical sign has to be long enough, just like mine now, with a little tail at the end. Here is another example. The way it's written could be misleading. Did you mean a square root of 2 divided by 4? Or did you mean the square root of the expression 2 divided by 4? To be clear on this notation, please make sure that your radical sign is tall enough and again long enough, with a little tail clarifying who the radicand is. I would like to ask you to generate a list of the first 10 perfect square numbers, beginning from the smallest one. To help you understand how it's done, I'll go back to the origin of perfect square numbers. If you think about a square where the measure of one side is 1 and the measure of the other side is 1, then to find an area of such square you would have to multiply length and the width. So when you multiply 1 times 1, the result of course is 1. Therefore 1 received the name of a first perfect square number. Next perfect square number could be received by multiplying 2 and 2. The result would be 4. And of course we will continue in increments of 1. 3 times 3 will produce a 9, and I'm sure you can finish this list. All these numbers in green right here are called perfect square numbers. I usually advise that you know by memory the list of all perfect square numbers up to 14 times 14. So 10 times 10 would produce 100, 11 times 11, 121, 13 times 13, 169, 14 times 14 is 196, And yes, of course, I skipped 12 times 12 for no good reason. The result will be 144. I want you to make one more generalization about the expressions we just produced. Please recall that 2 times 2 could be written as an expression with an exponent, 2 to the power 2. Can you finish a similar expression for 3 times 3, 6 times 6, and 7 times 7? We will use these expressions to explain how and why square root of perfect numbers produce certain values. I would like to build up now on the material that we just discussed. What if my square has sides expressed as a variable, x and x? How would we find the area in that case? Well, we would multiply x and x, where the result would be x squared. So let's bring us a little further. What if the side measures x to the second power and x to the second power? What would be the area in those terms? X to the second power times x to the second power produces x to the fourth power. And one more example. What if my sides measured as x to the third power and x to the third power? What would be the area then? The result will be x to the second power. You might ask me why, and I will remind you that x to the third power is written as x times x, and now you're multiplying it by another x to the third power. So this expression produces x to the fourth power. What we just generated is a list of perfect square variables, and as you see, they grow by 2. That's a very important generalization that will serve you later in algebra course. I would like to move on and show you how a list of perfect square numbers is used to simplify expressions. I will start with the simplest expression, square root of 4. We know that positive square root of 4 equals 2. But why exactly is that so? Well, I would like you to look at the generalizations that we received earlier. I'm going to copy the square root sign, but rewrite 4 as a 2 to the second power. That is so that I now can point out that we have two opposite operations, raising something to the second power and taking a square root. Since they are opposite operations, they cancel each other, and the result becomes 2. I'd like to invite you now to use these simple facts to simplify an expression, square root of 9. You may pause this video. Okay, just like in the previous example, I will rewrite 9 as a square of 3, all under the square root. Then a square and a square root will cancel each other, producing the result of 3. One more example. Square root of 49. It would be a square root of 7 to the second power. Therefore, it will simplify to a 7. So what exactly will happen if we take a square root of x squared? Well, exactly the same thing will happen. Raising something to the second power and taking a square root will be two opposite operations. They will cancel each other, and the result will be x. In fact, what we just derived represents a very convenient rule that states that if you have a number raised to the second power and take a square root out of it, the result will be the number itself.